Hello class, this is a continuation of lessons dealing with solution stoichiometry. In our last lesson, we briefly discussed the background ideas behind precipitation chemical reactions, and we discussed the terms precipitate, which is our insoluble solid that forms when two aqueous solutions are mixed, and we discussed gravimetric analysis, a laboratory technique used to separate mixtures with aqueous and solid components. We also briefly discussed our solubility rules, but we did not get to put them into practice. So we're going to pick up there and look at exercise 7. In the memorize this box, it says all sodium, potassium, ammonium, and nitrate containing salts are soluble in water. All halide salts, salts that have a halogen such as fluorine, chlorine, bromine, or iodine, are soluble except when bonded to silver, mercury, or lead. So let's put this into practice. Essentially, in this problem set, it says using the solubility rules, predict what will happen when the following pairs of solutions are mixed. We are given our reactants here, so essentially we need to predict the products and then identify if they will be aqueous or solid. So here, I know that potassium and barium will either stay in the same place or nitrate and chlorine will stay in the same place. It doesn't matter which two you switch, as long as you switch an anion with an anion or you switch a cation with a cation. I'm going to keep potassium in the same place, and I'm going to switch nitrate and chlorine. So to do this, I need to check my charges. I see +1, -1. Those are balanced, so the correct formula when potassium bonds with chlorine is KCl. I'm going to open up some parentheses and leave some space there for my phase designations. Then I have barium, which is a +2 charge. Oops. And I have nitrate, which is a -1 charge. To balance this, I need 2 nitrates to balance out my +2 charge for barium. And then same deal, parentheses, and then we can figure out, based off of our solubility rules, what the phase designations are. I do need to balance this equation. So I see 2 chlorines on the left. I know I will need 2 chlorines on the right. And as a result, that doubled my potassium. So my coefficient of 2 also goes in front of potassium nitrate. And then it becomes a 1 in front of my other components. So if I apply my solubility rules, I see that I have a potassium and a halide. Both of those types of salts are aqueous, so this is definitely an aqueous compound, no matter how you spin it. So we're going to write AQ. Barium does not pop up in our list anywhere, but it does say that nitrate-containing salts are soluble. There is nitrate here, so this one will also be aqueous. So when these two solutions are mixed, we wouldn't see any observable solid forming in the bottom of our container because both products remain aqueous. Let's try the next one. I'm going to go ahead and switch places here. I'll try doing it with cations this time because it doesn't really matter which way you switch. You can switch cation for cation or anion for anion. I did anions last time, so I'll switch cations this time just to show you that it doesn't really matter. Lead, we'll have to figure out its charge in a minute, is going to match up with sulfate. And sodium is going to match up with nitrate. Nitrate and sodium is +1, -1, so those charges are balanced. And it is both a sodium and a nitrate containing salt, so this is definitely going to be aqueous. We have to look back at the charges here for lead nitrate to figure out my charge for lead. Remember, this is a transition metal. If I have two -1s, because there are two nitrates, then lead must be a +2. So the charge does not change during a precipitation reaction or a double replacement reaction. Lead still carries a 2+ charge when it bonds with a new substance. Sulfate has a -2 charge. Those are balanced, so that stays the same. So we have our correct formulas. We just need to balance here. I had two sodiums on the left. I need a 2 here to balance that out. I also had two nitrates on the left, and this also balanced that out. So I get 1, 1, 1, 2. Now I just need my phase designation. Sulfates and lead are not mentioned in our solubility rules, other than saying that lead typically is an insoluble compound. So this one would form a precipitate in the form of lead sulfate. So you could expect to see some sort of solid appearing in the bottom of your container when you mix these two components. Let's do one more. Here, let's do the work first to figure out our charges. If I have three -1s from nitrate, iron must be a +3 here. So when I do my double replacement, I get KNO3, that's +1 -1. Those are both potassium and nitrate salts there, so that's aqueous. And then I get FeOH, which is +3 and -1. I need 3 hydroxides to balance that out. Oops. And this does not have a sodium, potassium, ammonium, or nitrate containing salt, nor does it have a halide. So this would also be a solid. The last thing we have to do is just balance. I need 3 nitrates, 3 potassiums, and 3 hydroxides. So the balance is 3, 1, 3, 1. Okay, go ahead and try to do the same on You Try It, set 7. Remember to keep in mind that silver, lead, and mercury containing salts are typically insoluble when they have halides bonded to them. Okay, so an extension of what we just learned looking at solubility rules is the different ways to describe reactions in aqueous solution. There are 3 ways. The way we just did was the complete balanced equation. This gives the reactants and products and the overall reaction stoichiometry, but not the forms of the reactants and products as they exist in solution. What I mean by that is that we have to consider the dissociation that occurs when an ionic compound that is aqueous dissolves in water. Previously, we looked at things that are aqueous dissolving. So, for example, NaNO3, if it is aqueous, in reality, it exists as Na plus ions and NO3 minus ions that are separate in the solution. And you've seen some diagrams previously that showed us that. So if I scroll back up, here we go. These particle diagrams, you can see some things are just floating around as ions in solution. You've got nitrate ions, you've got potassium ions. The barium and chromate ions have bonded together and don't remain aqueous in solution. But for the things that are soluble, they are free floating and dissolved in water. So we need a way to represent that. For that, we're going to use the complete ionic equation. This represents all reactants and products that are strong electrolytes, aka things that can dissociate, as ions. When we represent them as ions, we're going to split it into the 2 parts, the positive cations and the negative anions. You must show charges here for a complete ionic equation. We also have the net ionic equation. Just like the term net worth, the net shows us just the relevant components at the end of the reaction, or rather, the things that are undergoing a chemical change. We don't include spectator ions in a net ionic equation. A spectator ion is just something that is not involved in the reaction process. It started as an ion on the reactant side and finishes as the same ion on the product side. It remains chemically unchanged. There is always a conservation of mass and charge in net ionic equations. If all products are soluble, there is no net ionic equation, just balanced and complete ionic equations. So we're going to do some examples together, and we're going to show all three. So I give us a written chemical equation. It tells us we have aqueous potassium chloride, and it is added to aqueous silver nitrate to form silver chloride precipitate, meaning solid, and aqueous potassium nitrate. So here I've got KCl, aqueous, plus AgNO3, aqueous. Here, let me zoom in on this so I have a little more space. Let's go full screen on this one. There we go. Whoa. So we're going to work through all three: balanced equation, complete ionic equation, and net ionic equation for this problem set. So with this first one, we have aqueous potassium chloride added to aqueous silver nitrate. Same deal, we have to check our charges, +1, -1. They tell us it is aqueous. AgNO3, +1, -1, so that's balanced, and that's also aqueous. And then it forms silver chloride, AgCl, +1, -1, but they tell us it's a precipitate, so it is a solid. And then aqueous potassium nitrate, KNO3, +1, -1, and that is also aqueous. Thankfully, this is a really easy one to balance. We only have 1 mole of each component. So to show the complete ionic equation, we're going to split these aqueous components into their respective ions with their charges. Now, the solid cannot split up because it is now part of a different phase. It is not surrounded by water, and it is not aqueous in solution. So when we put these together, we get 1 mole of K plus aqueous plus 1 mole of Cl minus aqueous, 1 mole of Ag plus aqueous, and 1 mole of NO3 minus aqueous. On the product side, AgCl stays combined because it is a solid, but the 1 mole of KNO3 splits up into 1 mole of K plus and 1 mole of NO3 minus. So we have written a complete ionic equation here. Notice that the charges balance out. There's a conservation of charge and a conservation of mass because it's still a balanced chemical equation. Now let's identify our spectator ions. Spectators are things that are unchanged from the reactant side to the product side. Here I see K plus is the same on both sides, and NO3 minus is the same on both sides. When we write our net ionic equation, we will leave those components out. So we will bring down the other components. 1 mole of Cl minus and 1 mole of Ag plus forms 1 mole of AgCl solid. So in a way, there's some similarities to the dissociation equations we saw in our previous lesson. The dissociation equation usually shows the aqueous component splitting up into its ions. Here we show the ions coming together to form a solid precipitate. Okay, let's do a time check. All right, let's do one more example, and then we'll have you try some on your own. So I like that color scheme. We'll do purple for our balanced equation. We have aqueous potassium hydroxide, which is +1 -1. So that stays balanced. Mixed with iron 3 nitrate, which is aqueous. Nitrate is -1. So we need 3 nitrate to balance that out. And then it reacts to form iron 3 hydroxide. Hydroxide, again, is still -1, so we need 3 of them. That's our solid, plus aqueous potassium nitrate, KNO3, +1 -1. Now, when you write your balanced chemical equation, you don't actually need these charges here. I should have mentioned that before. You only need them when you're writing the formulas, and then you can get rid of them. However, I left them in the last problem because it made it a little bit easier to write my complete ionic and net ionic equation. I didn't have to refer back to check my charges. Before we can move on to complete ionic equations, we have to make sure we are balanced. So I need 3 moles here to balance out my 3 OHs on each side. I see I also have 3 nitrates on the left, so I need 3 nitrates on the right. And that also balances my K. So this is my balanced chemical equation. So again, we're going to take the aqueous components and split them up into their charges. Their charged ion components, and we're going to leave our solid alone. So here, I've got 3 moles of K plus aqueous and 3 moles of OH minus aqueous. Now, it's important to note that the 3 applies to both of these ions. I have 3 moles of each when they split up. When iron nitrate splits up, I have 1 mole of Fe plus, or Fe3 plus, sorry. But I actually have 3 moles of nitrate ions because of the 3 on the outside of my parentheses here. So I have 3 NO3 minus. That's the tricky part about ionic equations, is keeping track of the stoichiometry. I end up with 1 mole of FeOH3 that stays solid. And then I get 3 moles of K plus. Sorry, minor computer glitch. Aqueous, and 3 moles of NO3 minus, also aqueous. This would be my complete ionic equation. Notice I also applied the 3 to both of these, so 3 moles of K plus, 3 moles of nitrate. Now let's look for the things that are common on each side. I see 3 moles of K on each side, and I see 3 moles of nitrate on each side. So those are going to be left out of my net ionic equation. So my net ionic equation ends up being 3 moles of OH minus that are aqueous and 1 mole of Fe3 plus that is aqueous. reacts to form 1 mole of FeOH3, and that is a solid. Okay. Go ahead and try set 8, where you go through, and I think I have a couple of different examples here, or practice problems to work on. In our next lesson, we'll cover calculations involving gravimetric analysis of mixtures by precipitation reactions. Have a great day.